Okay, let's unpack this. Imagine you're standing before just this huge amount of information, maybe a new field you need to get up to speed on for work, or just some complex topic you find fascinating.
Right.
You want to dive in, really get a solid grasp, but quickly,
Yeah.
without
Well,
getting totally bogged down in jargon or just lost in disorganized stuff online.
yeah, that feeling of information overload is pretty common.
Exactly. So today, we're doing a special kind of deep dive. We're not just exploring a topic in general. We're focusing on one specific, really valuable resource.
Mm.
The book, Supervised Machine Learning with Python by Ahmed Khorshid.
Mm.
We're basically giving you a guided tour of how this book tackles the subject, how it sets you up for a complete learning journey. It's kind of a benchmark for a great educational resource, I think.
That's a great way to put it. What's really compelling about this book and why we're focusing on it is that it's not just like a random collection of facts or code.
Right.
It's been meticulously designed as a complete learning experience, building things up chapter by chapter.
From the ground up.
Pretty much. From the real basics right through to some quite advanced topics, but always with this strong focus on actually doing it, practical implementation using Python.
Okay, so the promise here is that by the end of this, you, the listener, will have a really clear roadmap of the key ideas, the tools you need, the applications, all framed by how this particular book lays it out.
Exactly. A comprehensive look inside a well-structured guide.
So where does this resource start? How does it begin to demystify supervised machine learning?
Well, it starts right at the beginning, defining what supervised machine learning actually is.
Okay.
The book uses a good analogy, like teaching a child to recognize a cat. You show them pictures, and crucially, you label each one. This is a cat.
So the supervised part is the label, the correct answer provided by the teacher.
Precisely. The model learns from this labeled training data. The book then highlights sort of 3 core ideas that really define supervised learning.
What if?
First, it's about input-output mapping. The model learns a function, basically fx, mapping inputs like that cat picture x, to an output, the label y.
Got it. X to Y.
Second, and this is critical, you absolutely need labeled data for training. No labels, no supervised learning.
Okay, makes sense.
And third, the ultimate goal isn't just memorizing the training data, it's generalization. The model needs to perform well on data it's never seen before.
Like a student applying knowledge to new problems, not just repeating answers.
Exactly. And the book immediately clarifies the 2 main types of problems you'll tackle. Regression.
Which is predicting numbers, like house prices.
Right, continuous numerical values. And classification.
Predicting categories like spam or not spam, or maybe identifying different types of animals.
Perfect examples. Spam detection, image classification, those are classic classification tasks.
Now, something I found really insightful, especially for anyone who wants to actually build things, is how the book immediately makes the case for Python. Why Python?
Yeah, it doesn't just assume you know. It explains why Python is basically the go-to language here. It points to its incredibly rich ecosystem of libraries.
Like having a massive, well-organized toolbox ready.
Exactly. Plus, its syntax is relatively straightforward compared to some other languages, and it integrates really well with other data science tools. It's just practical.
Okay, so it establishes Python's role. But what tools specifically does it say you need?
It gets right into that. No messing around. It introduces the absolute essentials straight away. You've got NumPy.
For numerical stuff, right? Arrays and maths.
Yep, fundamental for efficient computing. Then Pandas, which is your powerhouse for data manipulation and analysis.
I live without Pandas.
Pretty much. Then Scikit-learn, which is huge. It provides a vast collection of machine learning algorithms and tools.
The workhorse library.
Definitely. And for seeing what's going on in your data, Matplotlib and Seaborn for visualization.
Visualization is key.
Absolutely. And what's really helpful, I think, is that the book actually walks you through setting up your Python environment properly. It even covers using virtual environments.
Oh, that's good. Managing dependencies can be a nightmare otherwise.
Totally. So it ensures you start off on the right foot, avoiding those common setup headaches. It really shows how a well-thought-out book anticipates the learner's needs.
All right, so you understand the basics, you've got Python set up. What's the next big hurdle the book helps you tackle?
Data. It's all about the data.
The messy part.
Often, yes. Raw data is rarely perfect. The book uses the analogy of recipe ingredients, some missing, some wrong measurements.
Some just weird.
Exactly. So the book dedicates serious attention to data preprocessing. It makes it clear that this isn't optional. It's crucial.
Why so crucial?
Because fundamentally, poor quality data leads to unreliable models. It's that classic saying, garbage in, garbage out.
Right. So what kind of garbage does it help you clean up? Missing data must be a big one.
Huge. It's a universal problem. The book outlines different strategies. Sometimes simple deletion works, like removing rows if only a tiny fraction of data is missing, maybe less than 5%, or even dropping a whole column if it's mostly empty.
But you can't always just delete data, can you?
No, definitely not. So it dives into imputation, filling in the gaps. You've got basic methods like using the mean or median for numbers or the mode for categories.
Okay, the simpler stuff.
Yes, but then it also introduces more sophisticated techniques like k-nearest neighbors imputation or KNN imputation.
How does that work?
It basically looks at the neighboring or most similar data points to the one with the missing value and uses them to make an educated guess. It can even cover regression imputation. The key takeaway isn't just listing these, but giving you the context to choose the right method.
And it's not just about filling gaps, right?
Yeah.
What about features that are on totally different scales, like age in years versus income in thousands?
Good point. That's another major preprocessing step, feature scaling and normalization. The book tackles this head on.
Yeah, I remember being confused about when to use standard scalar versus min-max scalar. Does the book clear that up?
It does a really good job. It explains that standardization or z-score normalization transforms data to have a mean of 0 and a standard deviation of 1.
Okay, why is that important?
It's crucial for algorithms that are sensitive to feature scales, like SVMs or PCA. Without it, features with larger values could unfairly dominate the learning process just because of their scale, not their importance.
Ah, I see. And min-max scalar.
That scales data to a specific range, usually 0 to 1. This is often preferred for things like neural networks or distance-based algorithms like KNN, where you need features within a fixed boundary.
Makes sense. Different tools for different jobs.
Exactly. And importantly, the book weaves exploratory data analysis, or EDA, into this whole process, using Pandas for stats and Matplotlib and Seaborn for plotting histograms, scatter plots, correlation heat maps.
So you actually look at your data first.
Yes. It emphasizes getting to know your data intimately before you start modeling, visualizing distributions, spotting relationships, or outliers. It's a vital step that's often underestimated.
Okay, data's clean, prepped, understood. Now, for the exciting part, right? The algorithms. How does the book introduce these?
Yeah, this is where you start building the models. It begins with a general overview in one chapter, laying out the components, and then dives into specific types of algorithms over several chapters.
So it builds up the arsenal gradually.
It does. For instance, it covers binary and multi-class classification. It explains logistic regression, which, despite the name, is for classification.
Like spam detection you mentioned earlier.
Exactly. And it shows how to extend it beyond just two categories, using methods like one versus rest or the softmax function for multi-class problems.
And just predicting correctly isn't enough, is it? How does it cover evaluating these models?
That's a key strength. It stresses going beyond simple accuracy. It explains the confusion matrix in detail and metrics like precision, recall, and the F1 score.
Why are those so important?
Because they give you a much more nuanced view of performance, especially if your classes are imbalanced, like detecting rare diseases, where just being accurate overall isn't good enough. You need to know how well you're catching the rare cases.
Okay, what about other popular models? I hear a lot about tree-based models. Are they covered?
Oh, yes, definitely. They get good coverage because they're powerful and often quite interpretable.
Interpretable how?
The book explains decision trees first. They work by making a series of splits in the data, almost like a flowchart of if-then-else rules. It explains the math behind choosing the best splits, using criteria like Gini impurity or entropy.
So you can kind of follow the logic.
To some extent, yes, but then it moves to random forests. These are fascinating. They're an ensemble method.
Ensemble, meaning multiple models working together.
Exactly. A random forest builds lots of individual decision trees, but each tree is trained on a random subset of the data and a random subset of the features. This process is called bagging.
Why do that?
It's incredibly effective at reducing overfitting, the tendency of a model to memorize the training data too well and fail on new data. Random forests are much more robust than single trees.
So, the wisdom of the crowd, applied to trees.
A great analogy. And the book doesn't stop there. It gets into gradient boosting machines, or GBMs.
Which leads to things like XGBoost. I hear that name a lot.
Absolutely. There's a whole chapter dedicated to XGBoost later on. It's a highly optimized gradient boosting algorithm, famous for winning data science competitions. The book explains why it's so good at speed, built-in regularization to prevent overfitting, and how it handles missing data cleverly.
Wow, okay. That's quite a range. Does it also get into neural networks? That seems like a whole different beast.
It does. It introduces them through multilayer perceptrons, or MLPs, which are sort of the foundational type of feed-forward neural network.
How does it make those understandable? They seem like black boxes sometimes.
It breaks down the architecture clearly. The input layer, the hidden layers where the computation happens, and the output layer. It explains the role of activation functions like ReLU, sigmoid, softmax, which are crucial for letting the network learn complex, nonlinear patterns.
Things that simpler models can't capture.
Exactly. And crucially, it explains the two core mechanics. Forward propagation, which is how the network makes a prediction.
Data flows through the layers.
Right. And back propagation. This is the learning part. It's how the network adjusts its internal connections, its weights, based on the errors it makes, propagating that error signal backward through the network using calculus, specifically gradient descent.
Okay, that sounds complex, but important to grasp.
It's the engine of deep learning, really. The book also covers other important algorithms like support vector machines, or SVMs.
What's special about them?
Their goal is to find the optimal boundary, the hyperplane, that best separates different classes, maximizing the margin between them. And it explains the kernel trick.
The kernel trick sounds mysterious.
It's a clever mathematical technique that allows SVMs to handle nonlinear data efficiently by implicitly mapping it to a higher dimensional space where it can be separated linearly. Very powerful. It also touches on probabilistic models like Naïve Bayes and instance-based learning like k-nearest neighbors, KNN, showing their different approaches.
Okay, so you've got your data prepped, you've picked an algorithm, maybe trained an initial model. What's next, according to the book? Surely it's not perfect right away.
Rarely. So the next phase is all about refining that model and understanding it better. A huge part of this is hyperparameter tuning.
Tweaking the settings of the algorithm itself.
Precisely. The book clearly explains two main strategies. Grid search.
Which tries every possible combination. Sounds slow.
It can be, especially if you have many parameters. It's exhaustive. That's why the book also explains random search.
Which just tries random combinations.
Yeah, it samples randomly from the parameter distributions you define. Often, it finds very good combinations much faster than grid search, especially in high-dimensional spaces or if you have limited time or computing power. The key insight is knowing the trade-offs.
And you need to evaluate these different settings properly, right?
Absolutely. The book stresses using cross-validation throughout this tuning process. That ensures your performance metrics are reliable and not just down to luck on one particular train test split.
What about dealing with data sets that have just too many features? Hundreds, maybe thousands. Does that cause problems?
It definitely can. It's known as the curse of dimensionality. High-dimensional data becomes sparse, distances between points become less meaningful, and models can struggle or become computationally expensive.
So how does the book suggest tackling that?
Through dimensionality reduction techniques. It covers the classics like principal component analysis, or PCA.
What's PCA do?
It's an unsupervised technique that finds new axes, the principal components, that capture the maximum variance in the data. It lets you reduce the number of features while retaining most of the important information. Great for general feature reduction.
And others.
Yes, it also explains linear discriminant analysis, or LDA. Unlike PCA, LDA is supervised. It specifically tries to find a lower dimensional space that maximizes the separability between known classes. So it's really useful when your goal is classification.
Okay, so PCA for general reduction, LDA specifically for classification problems.
That's a good summary. The book even mentions techniques like TSNE and